Okay, I'm skipping over to OpenStack's Calculus 3 just for a little bit. We're talking about multiple integration here, so let's go through a little bit of a PowerPoint before we do anything else here. Now, let's take the following situation. I've got z as a continuous function of x and y. So this forms a nice continuous surface over the rectangle R that you can see there. Okay. R is in what? A rectangle in the xy plane, of course. All right. Now let me ask you the following question here. Suppose I was interested in trying to find the volume of this bluish looking figure that is formed by the surface z equals f of xy on top, bounded by the rectangle R. What would you do as an approximation? Well, here's one idea of what we might do here. Might come over here and imagine partitioning up that rectangle R into a bunch of subrectangles, and then going ahead and taking sample points in each of those subrectangles, and then what? Evaluate the function there, and then what? Find that would form a bunch of little thin rectangular boxes above each subrectangle, and then find the volumes of those, and then add them all up. That's exactly what we do to get an approximation for the volume of this figure here that you can see. Okay? Now, what about the exact volume, not just an approximation? Well, what we do is make sure that the norm of the partition, that is, the area of every single one of these rectangles, has the quality that both its length and width goes to 0. Effectively, that would amount to making sure the norm of the partition in both the x and the y direction goes to 0. And that's how we actually define the volume underneath our surface. Okay? This is what we would call a double integration. All right? Now, we're going to see some more along these lines here in a second. Back and talk about the partition of the rectangle R again. You guys notice here that in the drawing, they've actually partitioned up what? The interval from A to B in the x direction and the interval from C to D in the y direction here. You can see these little vertical lines going up from the x-axis and the horizontal lines coming off the y-axis. Okay? They suppress the fact that you would probably use x sub 0 as, or x naught as a, the original value here. Okay, for of x. Anyway, let's say we partitioned the interval from A to B into n subintervals, and the interval from C to D in the y direction into m subintervals. That gives us n times m subrectangles. Okay? Now, what would be a good notation for those subrectangles? Well, the first thing you could consider is r sub ij. What does that mean? Why am I using a double subscript? R sub ij refers to the rectangle obtained by what? The ith subinterval in the x direction by what? The jth subinterval in the y direction. Likewise, we have what? X sub, take for example, well, let's do this. X sub ij, y sub ij, that's the sample point in the r sub ijth rectangle. Okay? We're using that double subscript notation as a convenience there. Okay? So I hope that makes good sense to you why we're using a double subscript here. Now, I'm going to go to the document cam, and I'm going to talk about actual calculations along these lines in a second here, and let's see how that works.